Alrighty, so now we are moving to the front of the textbook. So we're on chapter 1 now. Um, and the first section that we are going to be reviewing is 1.3. So I don't think we ever really discussed 1.1 and 1.2, but it's, in my opinion, just fluff. We don't really need it. It's not really math oriented, in my opinion. So 1.3 is all about equations describing relationships in data. So we're kind of building the ground up right now. So we're first going to talk about making linear models from data. I'm going to give you some data, and eventually you will be able to create an equation out of it, or a model, basically. Y equals mx plus b, pretty much. All right, so in the real world, you collect data and want to use the data to make predictions about informations that you didn't collect on data. So I'm kind of giving you just a background of like why it's important to do this instead of we're doing this. Okay, so imagine you want to know the pressure of the underwater. Okay, not that relatable, but maybe what if you, I don't know, you go scuba diving and collect data by measuring the pressure difference in depths. You use this data to create a model, i.e. the relationship between pressure and depth. So I have all my depths and I have all my pressures. And with the depth at 0, 10, 20, and 30, I measure these for pressures. So then eventually, after we go through a few of these sections, you guys are going to be able to take this data and we're going to make a model. And we'll eventually learn how to make a model. And most of our models are going to look kind of something like this. We'll have P, that's going to denote our pressure, equal to 14.7 plus 0.45. And we'll talk about how we get this and the different components of this equation later on. Because I'm just setting up. Eventually, you'll be able to go from here to make a model to get to here. And then with this model, I can go down and see that when the depth is 200, I can figure out the pressure. And thus, I can predict what the pressure would be at 200 feet depth. Okay. So if P is pressure and D is depth in mathematics, it's pretty common to name your variables the first letter of what they're describing. Just really keeps everything pretty succinct. So we can now use our model to predict the pressure at 200 feet deep, right? So if I want to know at 200 depth, I would put 200 instead of the letter D, so that the pressure be 14.7 plus 0.5 times 200, which would equal approximately 104.7. And then we're going to be talking a lot about real world problems. So we always have to give units on our answers. Without any units, it's like when an officer pulls you over, like, how fast are you going? You're like 4. What does that mean? Like, I don't know. So you got to give some units. Okay. So that's kind of the broad picture of what we're going to be doing in this chapter. Not even just this section, like the chapter as well. Okay. Taking data, making a model, and doing predictions with it. So what is a model? A model, am I recording? Okay, thank God I am, is a mathematical representation of a real world situation. A linear model is of the form y equals your textbook has it written one way, and we'll do it that way. A plus bx. All right, where A is our initial value. And initial, kind of think about like that's when like time equals 0. So just when x equals 0. So x equals 0. And we can kind of see that, right? Like if x equals 0, well, then this whole thing is 0. So then you just get y equals a. So that's your initial value. Oops, didn't want to delete that. I want to delete this. B is, so we add B for each, oh my God, I can't spell. Change in Y. Sorry, change in X. So X goes up by 1. Then I add B is the change to Y when I increase X by 1. Okay? If I want to increase X more, I would multiply B by that number. Or less. Okay? So let's do an example. So a furniture collects the below data. So he makes X number of chairs and it'll cost him C dollars. Okay? So if he makes 0 chairs, it still costs him $80, right? Lights, rent for the building, materials that he hasn't used yet, yada, yada, yada. And at 1, 92, at 2, 104, at 3, 116, and 4, 128. So we're asked to find a linear model for making X chairs. Okay? So we can see that every additional chair costs how much? So from 0 to 1, that would be from 80 to 92, that would be 12. From 92 to 104, that would be 12. From 104 to 16, it's 12 each time. $12, I really should say. So each additional chair costs $12. All right. So I change X1, the price goes up 12. So B, sorry, excuse me, the cost goes up 12. So B is 12. A is the initial cost. So the cost of making 0 chairs. So I go over 0 and it costs $80. So that means A is 80. All right, thus, I'm not using Y here. C is my output. So C is in dollars. So C equals 80 plus 12x. Okay? How could I check that this is right? I could just check by plugging in some of these x's. So let's say when x equals 2, so C would equal 80 plus 12 times 2, which would be 80 plus 24, which would be 104. Oopsies. And I could see when the cost is 2, sorry, when I'm making 2 chairs, the cost is 104. Perfect. So that's a way to check. I wouldn't check 0 because we already chose that would be 80. So it's again kind of trivial. All right. So now we're asked to graph the model. So when it comes to graphing things, we need to draw our axes, which is basically like the real number line, where one is horizontal, one is vertical. Ooh. So we need to draw our arrows because those keep going forever. I like to label my axis. So this is going to be X and this is going to be C. And then we'll do like 1, 2, 3, and 4. I think that's the most that we do, right? 4. All right. And then we'll call each of these ticks plus 12. So this will be like 80, 92, 104, and so on, right? So, oh, that's a 0 and that's 1. So this is our first point, and then our second point, and then our third, and so on, right? Fourth would be like up here or something. Great, and then I would just, oh, that's really good. Draw a line like that. So you see that when I graph those points, I got a line. That's another description of a linear model, is that its graph is a line. The word linear has the word line in it. Okay? So that is our model. We can tell that the data satisfies linear model if there is what is called a common difference. Oops. In other words, if there is a difference in any two successive data points is the same, we can create a linear model. So we saw that so making from 0 chairs to 1 chair, $12 change. 1 to 2, $12. So each of these differences is the same. So their differences, they're in common. So common difference. Okay? Whee! So the temperature at very elevation has been recorded by a hiker. So the temperature is in Celsius, elevation is in kilometers. Excuse me. So we're asked to show that this data satisfies a linear model. Okay, well, elevation, temperature, I'm just want to write this real fast. I like to do this in terms of a chart. So 0, 1, 2, 3, 4, and 5, 20, 10, 0, -10, -20, -30. And then I can create a third column called common difference. So let's call it CD. Obviously from this first spot, we're not going to have anything. There's nothing 0 and 1. I'm going to compare. So I'm going to put that right down here. So the common difference between 0 and 1, 10, 20 minus 10 or 10 minus 20 if you wanted to. No, wait, no. I would do, so I'm going from 20 down to 10. So it's going to be positive 10 or negative 10. It's going to be negative 10. And we'll get another tool to make sure that's a little bit more clear, but not quite yet. We're just kind of thinking about it on our own right now. So then if I'm going up 1 kilometer to 2 kilometers and the temperature goes from 10 degrees to 0 degrees, that's also going down. The common difference there is, or the difference there is negative 10. It's going down. And then we keep seeing that. Great. So then we can say that the common difference is negative 10 degrees Celsius. So the data satisfies a linear model. Oh, degrees Celsius, right? We're answering a word problem, so we need to include our units. Okay, so now we're asked to find the linear model between temperature and elevation. Okay, cool. Good thing I wrote this chart again, so I don't have to scroll up. So, let's call our equation like E for elevation. Oh, wait, no. It would be temperature. It's going to be A plus B times the elevation. You can also do height, but meh, we'll just call it elevation. Okay, so when my elevation is, and we'll talk about in the next section, I believe 1.4 of how to figure out like who's on what side. How do I know which one's Y, which one's X? All right. Okay, which variable's over here and which one's over here. Think about who's affecting who. Does the temperature affect how high we are, or does how high we are affect the temperature? Okay. Since elevation affects the temperature, elevation is on this side and temperature is on this side. Okay, so our initial condition, our initial value is when we're at elevation 0, so 20. So A would be 20, and B is our common difference, how much we change each time, which is negative 10. Don't forget that negative, it's very important. So that means that t would equal 20 minus 10 times our elevation. And remember, we can always check that by plugging in an elevation. So like if we plug in 3, I'll get 20 minus 30, which will give me negative 10. If I had put positive 10, I wouldn't have not got the answer. I'd probably look back and see what I missed. Okay? So that's how we can kind of make a linear model from pretty basic data sets. Basic meaning x only goes up by 1 each time. So the point of making models is to make predictions, right? So a bathysphere, which is like this crazy contraption, there's a picture in your e-textbook. I would look it up. It's pretty crazy. Is lowered to the bottom of a deep ocean trench. If the depth pressure model is this one, this is what we talked about earlier, except I think I put 5 instead of 7. That's fine. What is the pressure at 30,000 feet? Right? So I want to be able to take this model. So P is 14.7 plus 0.47 D. And it says, what is the pressure at 3,000? So I want to find P when at 3,000 feet. So that sounds like a depth to me. So when D equals 3,000, how can I do that? I just plug it in. So P equals 14.7 plus 0.47. I know it's supposed to be 4.5, but that's fine. Times 3,000, which I actually don't know what it equal because my notes are different. Watching TikToks. 0.47 times 3,000 plus 14.7. And yes, there is pressure when we're at 0. That's called gravity. If there wasn't, we wouldn't be sitting here. We'd be floating here. So 1,014, no, not that much. 24.7. And then I would look, what is my pressure? I think before it was pounds per, that's in feet. What does it? You told me earlier. I didn't give it as detailed as a thing as what was in the textbook. Pressure pound per inches squared. Okay. Pounds per inches squared. Okay. And that's it. So that's how we can use our model to predict and how to use the data to kind of find a linear model. Okay. And there's a lot of study on taking data and finding models. It's actually a lot of my research and it's pretty fun. And it's pretty cool. So that's all for 1.3. Next is, or tomorrow will be 1.4, and that is the last section that will be on exam 1. All right, so I will see you there.